Look at a harvested field or a kitchen counter, and you will quickly notice that nature rarely delivers pure ingredients. Most of the world is a messy tangle of materials. But with the right forces applied, those messy mixtures burst apart into clean, uniform streams. To separate these materials, we rely on a strict rule. We exploit their physical differences. If two mixed materials have different sizes, weights, or magnetic charges, we can pull them apart. We do this without ever causing a chemical reaction or changing what the materials are actually made of. The easiest way to do this is by using the mechanical toolbox. This is a set of methods that relies on visible differences and physical motion to break things apart. If you can look at a mixture and identify a physical difference between the parts, you can usually force them apart using mechanical action alone. Handpicking is the simplest mechanical method of all. By looking at a handful of rice, you can spot small stones because they are a different size and color, allowing you to manually pluck the impurities right out. When manual picking is too slow, we use brute force. Threshing involves beating harvested crop stalks against a hard surface. The impact exploits a structural difference. The hard, edible grains break free, while the soft, inedible plant matter absorbs the blow. That leaves a pile of grain mixed with broken husks. To separate them, farmers use winnowing. By dropping the mixture from a height, they let gravity pull the heavy grain down, while the wind pushes the much lighter husk sideways. At the particle level, the physics are incredibly precise. Dense, heavy spheres have enough mass to overcome air resistance and drop straight down. Hollow shapes lack that mass, so the wind current easily catches and carries them sideways. If the parts of a mixture are all heavy enough to fall, we use sieving. Sieving only works for sorting dry, solid particles. Fine dirt easily slips through the gaps in a wire mesh, while larger, valuable artifacts are physically blocked and trapped on the surface. Sometimes we ignore size and weight entirely. Magnetic separation exploits an invisible property. A crane can hover over a massive pile of trash and pull jagged iron scraps straight up into the air, leaving paper, plastic, and non-magnetic metals completely unbothered below. The mechanical toolbox is highly effective for dry, solid chunks. However, if those solids are microscopic, or if they are suspended in a liquid, physical impacts and meshes become completely useless. This raises a problem. How do we separate a liquid filled with tiny solids that wind and magnets cannot touch? For this, we open the Density and Settling toolbox. The first tool is sedimentation. When mixed into a liquid, denser dirt particles sink to the bottom, leaving a clear liquid above. The second step is decantation. By carefully pouring the clear layer into a new container, the heavy sediment remains trapped. Sedimentation organizes the mixture by density, and decantation physically divides it. They are two halves of a single separation strategy. Gravity efficiently handles the heaviest particles, but it often leaves microscopic debris floating behind in the water. To catch those, we have to build a physical trap. To capture those floating solids, we follow decantation with filtration. A filter uses a barrier filled with microscopic pores to catch what gravity left behind. While sieving sorts dry solids by bouncing them over a rigid grid, filtration handles liquids. The fluid molecules flow easily through the microscopic gaps in the filter paper, while the jagged, insoluble solids hit a dead end and get stuck. The density toolbox is ideal for separating insoluble solids from liquids, but if a solid perfectly dissolves and becomes part of the liquid itself, it will slip right through the finest filter paper on Earth. So how do we separate an invisible, perfectly dissolved solid, like salt in ocean water? We have to move to the phase change toolbox. Instead of moving the solid, we move the liquid. By applying heat, we trigger evaporation. The liquid water turns into an invisible gas and rises into the air, forcing the mixture apart. A common misconception is that the dissolved solid vanishes along with the water. It doesn't. As the fluid molecules vibrate and fly upward as vapor, the salt molecules are left behind, locking together into a rigid, geometric crystal. Humanity relies on this exact process at a massive scale. By letting shallow ocean pits sit in the sun, the water evaporates into the atmosphere, allowing workers to literally rake up the salt left behind. If we want to keep the water instead of letting it float away, we use distillation. Distillation traps that escaping hot vapor and cools it back down into pure liquid water, a process known as condensation. When heat isn't the right option for a blended liquid, we use extreme motion. Churning rapidly spins a mixture like milk. The intense physical motion forces the lighter fat molecules to clump together and float to the top as butter, while the heavier liquid stays below. By manipulating the physical state of a material or by applying extreme forces, we can unmix even the most perfectly blended solutions. These basic principles power massive global industries. Crude oil refineries rely entirely on distillation, heating crude oil in massive towers to separate out fuels based strictly on their boiling points. Our own biology uses these rules. Your kidneys are a highly advanced filtration system, constantly separating waste from your blood. Early medical technology, like this vintage dialysis machine, was built specifically to mimic that physical separation. These methods are even used off-world. Space exploration relies on sieving to sort and analyze rocky samples from the lunar surface. Whether you are boiling tea, harvesting wheat in a field, or engineering a spacecraft, the strategy is exactly the same. You are exploiting the physical laws of the universe to sort a raw, messy world into the pure resources you need.